Okay, so we're going to look at specific heat. And I know that you've already had some encounter with this term before, but there's some new information to be had. So, yeah, let's look at that. So, specific heat is defined as energy required to raise temperature, energy required to raise temp of unit mass of substance by 1 in any specific way. This is just definition to give you an idea. Don't really need this. Unit is important, joule per kilogram Kelvin, because sometimes in the tables it might be given as kilojoule, so you have to convert it, or joule per kilogram degree Celsius. However, this is not used as much. This is the one that we use, right? For ideal gases, delta U equals to mCV delta T, delta H equals to mCP delta T. Now, what are Cp and Cv? So, specific heat, sorry, specific heat can be calculated either at constant volume or at constant pressure. This one is called Cv and this one is called Cp. So, Cv is equals to del U by del T at constant volume, and Cp is equals to del H by del T at constant pressure. I could show you the derivations of these, but personally I feel that they're not very important. However, if you do wish to take a look at the derivations, you can find the link of the notes in the description, and yeah, from there you can check out the derivations as well. But these will suffice. Okay, moving on. Cp is always greater than Cv due to extra PdV work. See, because Cv is calculated at constant volume, right? And if there's constant volume, there's not going to be any work. But since Cp is calculated at constant pressure, there is some PdV work. Also, Cp, Cv are properties of substance. Properties of substance. That is, they are point function. Not path functions, right? Now this next section is exclusively for ideal gases, because we mostly use these in context of ideal gases and liquids and solids. So be very careful to use these for ideal gases only. If a formula is applicable in general, I will write. As we saw, Cp, Cv, U, H depend on T only, nothing else. As Cv equals to del U by del T at constant volume, we can say U is a function of temperature only, and du equals to Cv dt, or delta U equals to mCv delta T. Now this is for constant Cv. That is, if your Cv is a function of temperature, then you will have to use this. But if your CV is of constant value, then you will have to use this. And you can only use these two formulas when we have ideal gas, right? Similarly, Cp equals to del H by del T at constant pressure. So H is a function of temperature and dH equals to Cp dt, or delta H equals to mCp delta T, right? Again, same conditions apply. Now we're going to look at something new, which is variation of Cp and Cv with respect to temperature for ideal gases. This is also called the empirical relationship of Cp with temperature. Empirical means that nobody knows why it's there, but experimentally it has been observed and verified, right? You don't need to remember this formula. This formula is also given on top of table 8.6. What you need to do is you need to know how to apply it. Cp with respect to temperature, variation with respect to temperature, is given by C naught plus C1 theta plus C2 theta square plus C3 theta cube, where theta is the given temperature by 1000 and C naught, C1, C2, C3 are obtained from table 8.6 for different gases. Also, we know that Cv equals to Cp plus R, or I remember it's Cv minus Cp equals to R. So we get Cv at constant temperature equals to this plus R, or yeah, this value plus R, right? And obviously you get value from the table. An extra formula we have here, H equals to U plus PV. This is for any substance, not only ideal gas. Although I've never actually used this, so and H equals to U plus RT. This is for ideal gas. And one last theory thing that I will talk about is specific heat ratio. You may also know this as gamma, is now denoted by small k, and it is Cp by Cv. Right. So, as we will see with the question, there are multiple ways of using the value of Cv and Cp. There's multiple values. You can use constant value, you can use value from table, you can use value at average temperature. There's tens of ways of using values of Cv and Cp by extension, right? So we're going to solve one question that's going to show us all of the ways of using the values. And when it is not mentioned what to use, you have to use your own brain to figure out what should you use. Okay, determine the change in internal energy of nitrogen in kilojoule per kilogram as it is heated from 600 Kelvin to 1000 Kelvin using empirical specific heat equation as a function of temperature. Remember, delta U equals to Cv delta T. However, this value is not constant here because we have to use the empirical specific heat relation, right? So we will use du equals to Cv dt. It's better you remember this and not this, because you can get this from this but not the other way around, right? So let me just write that one straight away. So keep in mind du equals to Cv dt. This is our first step. Then it is asking us to use the empirical specific heat equation, right? So if you remember, Cp equals to C naught plus C1t plus not t, theta, because theta is t by 1000. Theta plus C2 theta square plus C3 theta cube. So Cp is given by, if you get these values from the table for nitrogen, from table 8.6, you will get 1.11 minus 0.48 by 10 to the power 3 into t. I have converted theta into t by 1000 here, right? Plus 0.96 10 to the power 6 t square minus 0.42 by 10 to the power 9 t cube. And Cp minus Cv equals to R, which implies we want to put value of Cv in this formula, right? So we have to calculate Cv, which implies Cp minus R equals to Cv. So du equals to this term minus R dt. Now we want to find change in internal energy, right? And to find change in internal energy, what we will do is simply integrate this from T1 to T2, or T1 is 600 Kelvin and T2 is 1000 Kelvin, and you will get delta U to be 331.128 kilojoule per kilogram. That was the first way of using CPCV, using the empirical relationship that I have told you about from table 8.6. Using value of U as a function of T in the given data book. What this is basically asking you to do is to use the value of U from the data book, that is your thermo tables, and just plug in the values from there. I hope you understand by now how to use the thermo tables to find delta U. Obviously you can see the experimental value of U at 600 Kelvin, 1000 Kelvin, and just subtract those, right? So this is another way. So the answer will come out to be, for this, 329.95 kilojoule per kilogram Kelvin. Really simple, just refer to the thermo tables and do it. Part C. The constant C value at the average temperature. Okay, so it is telling us to use the value of C as a constant at the average temperature. So du equals to Cv dt, and as Cv is constant now, we can write this as delta U equals to Cv delta T, right? And it is telling us to use this value at the average temperature. So average temperature equals to T final plus T initial upon 2. So this will come out to be 1600 by 2, which is 800 Kelvin, right? So what we do is that to find the value of Cv at this temperature, we will again use the empirical relationship, right? But since the value of Cv is constant and it is to be found at some constant temperature, that is the average temperature, we don't have to integrate it, right? Because integration is for when Cv is changing with the temperature, so that we can account for the continuous change, right? That is what integration means. But here, since we have Cv value at constant temperature of 800 Kelvin, we will use the empirical relationship and just plug in T to be 800 Kelvin. So Cv is Cp minus R plus C1 into T by 10 to the power 3 plus, is C naught minus R plus C2 T square by 10 to the power 6. This is theta square, C3 10 to the power 3 by 10 to the power 9 theta cube, right? Cv value at 800 Kelvin will come out to be 0.82846, And delta U will come out to be 0.82846 into 1000 minus 600. So this should come out to be, let me calculate it for you, 331.384 kilojoule per kilogram Kelvin. Always write the right units because otherwise they will cut marks. Part D. The constant C value at room temperature of 25 degrees Celsius. Okay, again, two methods to do this. First, you can obviously use the empirical relationship. However, if you have noticed in the same table that you have your R values, the values of Cp and Cv are also given, and those are in fact at the room temperature. So, important to note, value of Cp, Cv at room temp are given in table A.5. So simply, and since it is constant, our du equals to cv dt gets converted into delta u equals to cv delta t, and simply plug in the value 0.744. It will be this at 25 degrees Celsius. 1000 minus 600 is the delta t, and it will come out to be 297.66 kilojoule per kilogram Kelvin. Okay, after this we have specific heats for solids and liquids, and that is quite important because sometimes they will ask an occasional question for it, and it's almost always a very solvable question. So after this we're going to look at that.